Those two objectives we hit yesterday were to describe the relationship between wavelength and frequency. So who can tell me the relationship between wavelength and frequency?
The higher the frequency, the shorter the wavelength.
Yes, so as we increase frequency, we shorten our wavelength because they are inversely proportional to each other. And then we were explaining why only certain frequencies of light excite certain atoms. This one's a little trickier, but we had some people who had the correct explanation. Would anybody care to take a stab at it?
You need more energy to excite the atoms. Like it requires a certain amount of energy.
Exactly. You require a certain amount of energy. So we use the analogy of the cans at the fair that you try to knock over. If you throw ping pong balls at it, doesn't matter how many ping pong balls you throw at it, you're not going to knock those cans over because you don't have enough energy. The same if you're trying to excite an atom with specific frequency of light. If that frequency of light is not high enough of an energy, then it's not going to excite the atom no matter how long you shine it at it. You have to reach the minimum frequency that has enough energy to excite it before you will. Okay. So, with that out of the way, we're going to pick up where we left off yesterday. So we covered these two, which means today we're covering our final objective, which is to describe Bohr's model of the atom. All right. So, we're going to talk a little bit about some experiments that were run to help show this model, and then we'll talk about the model itself. Scientists were still doing these experiments where they pass current through a gas at low pressure. If you remember, they did those with the cathode ray tubes, and that's how we discovered electrons. They're still doing those experiments, and they are noticing that the potential energy of those gas atoms is able to increase when they pass a current through it. So what they're doing is that current, that electricity, is giving energy to the atoms that are in the gas. Okay? So they start at what we call a ground state. This is the lowest energy state of an atom. So this is when it's not excited. So we talked about exciting an atom. This is when it's not excited. And there's only one ground state because you can't be less than not excited, right? Just can't be less than that. So there are excited states as well. So after they passed that electric current through it and gave energy, then they get excited. And those atoms can have more than one excited state, depending on the amount of energy that's put into them. So if they give them more energy, then they can go to a higher excited state. And if they give them less energy, then they'll go to a less excited state. When atoms return back down to their ground state, so when you stop giving them energy and they return back down to their ground state, they release that energy, and they release it as electromagnetic radiation. Sometimes that electromagnetic radiation is at the right wavelengths to be visible light. And so in that case, we would see the light. You guys saw this 2 days ago when we did our flame tests. So what you did was you excited those atoms, and then they emitted a specific color of light. Scientists expected, if they took an atom like hydrogen and they gave it an amount of energy, that it would be excited by any amount of energy, which we've already covered doesn't necessarily work. And the reason for that is because when you're exciting an atom, what you're actually doing is affecting its electrons. You're trying to, knock somebody's water over, sorry. You're trying to get it to release an electron. And some atoms hold on tighter to their electrons than others. In the same way that it would be maybe a little easier for me to take a football from Irene than from a linebacker, it requires a different level of energy. Okay? So they expected that any level of energy would do it, but they discovered that's not the case. The second thing that they expected to see is that if they gave it energy, that it would spit back out a wide range of light. So they were expecting a spectrum of light somewhat like a rainbow, where you had all the colors. Okay, so they gave this radiation to hydrogen, and then they discovered that that's not actually what happened. Instead of getting a rainbow of light back, what they got back was specific bands of colors. And for hydrogen specifically, they got back 4 specific bands of colors. They got like a red color, a greenish blue color, a blue, and a violet. So they only got back 4 colors. They didn't get any of the in-between ones. This suggests that for hydrogen, there's very specific spaces or levels of energy that electrons can exist at. And it takes different levels of energy to excite those electrons. That's a good question. Niels Bohr, a scientist, suggested a model of hydrogen to help explain why they were getting specific bands of color and not a whole range. Okay? What he suggested is that electrons exist in paths around the nucleus. So you have the nucleus at the center, and then there's these paths around the nucleus that electrons can take. This is called the planetary model, because if you look at it and you think about electrons being in these paths, it looks a little bit like our model of the solar system. Okay? So he suggested that these electrons could exist only in those specific paths or orbitals. So he was suggesting that they could not exist in the spaces between them. And he was saying that those 4 bands of light that we got represented 4 separate energy levels that the electron could exist at. But it can't exist anywhere in between. It can only exist at that specific level. When atoms are sitting in the orbital, they're not gaining or losing energy. But if they change orbitals, they either have to gain or lose energy. If they're going to gain energy, then they would move to a higher or a more excited energy state where they're further away from the nucleus. And if they lose energy, they're going to move back towards the nucleus, back towards their ground state. And as they're going back, they're going to release energy in the form of electromagnetic radiation or light. We'll come back to this last point here in a second, but first I want to take you out in the hall, and we're going to do a model of electrons absorbing and releasing energy to help this make a little more sense. So we're going to go to the stairs right out here in the hallway. You don't need to bring your iPads or anything, you can just come along. Okay, we're going to pretend that I'm the nucleus, and you guys are going to be electrons today, okay? And this staircase here is going to represent our orbitals, all right? So if you'll all stand on this bottom step here for me, you can be in your ground state. Or you can stand just slightly behind too if you need to. Okay?
We're just gonna pretend.
Not quite a big enough staircase. Okay, so you're at your ground state right now. You are not excited. Okay? But if I was to take and shine a light on you, which I didn't bring my phone with me this time. Last period I shone a flashlight at them and said that I'm giving you energy, then that would cause you to move up to the next energy level. So you can move up a stair if you'd like. And those of you who are down here can move up one. Okay? So now you are at an excited state. And if you were to come back down to ground state, you would emit energy in the form of light back at me. And the wavelength of that energy, or the frequency of that energy, would be equal to the amount of energy that you lost. So down here, you would have a lower frequency amount of energy than you would if you were up at the top step, right? So this wavelength of light will be lower frequency because there's less energy than the wavelength of light if you were in the 4th level of excitement. Okay? So down here, maybe we would have that red color because red is a lower frequency light. And up at the top, it might be more of a purple color. But you're not getting all of the colors in between because you just have one energy level, right? So that level of energy that you emit gives that specific wavelength of light. In the same way, if I asked you to stand in the air in between steps, could you do that for me?
No.
It wouldn't work, right? And that's the same for atoms in orbitals. They can't be between orbitals the same way you can't be between stairs. Or rungs on a ladder is sometimes even a better explanation, because here I could like put one foot up and one foot down. But if I asked you to stand in between the rungs of a ladder, you can't just hang in midair like that. So electrons can only be in their orbitals and not in between. If we hop back here, we can see that when Bohr went through the calculations and he calculated the energy levels for each of these orbitals, it matched the energy levels of the spectrum of light that the other scientists had found. So he went, great, awesome, this is a good model for how electrons are distributed in an atom. And then other scientists were like, awesome, let's try it with other atoms. And they moved on to other atoms and they discovered that it kind of starts to fall apart and it doesn't match up the same way. So what they learned was that when you have atoms that have more than one electron in them, because hydrogen only has one, then this model doesn't work anymore. So there's still a piece of the puzzle that we don't fully understand. And when we move on to the next lesson, we'll discuss that. But for right now, this model works for hydrogen, and it does help us understand a little bit of how electrons are distributed in an atom. Okay. So let's think back to Rutherford's model, right? He discovered that there was a nucleus in the center. That's very similar to Bohr's model. So Bohr did not change that. He said nucleus is in the center, right? Mm-hmm. Okay. How did his model differ from Rutherford's model? Instead of just having this nebulous cloud around the outside that says the electrons are here somewhere, we're not really sure where, he added orbitals, and he said the electrons need to be in one of these orbitals. That's where they're located. And then he was just very specific about they have to be in an orbital, they can't be in between them. So that touches our final objective, which is what Bohr's model of the atom looked like, which closes out our notes for today.
What is it?